Hello. So my name is Nabil Iqbal, and in this talk, I want to give you a very gentle introduction to the area in theoretical physics that is called holographic duality. So this is part one of two videos that will explain this, and the target audience for this is really undergrads in physics who've had exposure to maybe the first or second year of undergrad physics education. But I kind of think it should be accessible to pretty much anyone who has some exposure to the basic ideas in physics. Okay, so let's get started. These lectures are going to be about an idea called duality. So first, what is duality? Duality is when two things that look very different are secretly the same thing. So let me give you an example from elementary physics. Let's think about electrons. So when we first learn about electrons, we think that they are little particles, like little billiard balls that bounce around and do their thing. They move from here to there and they scatter off of each other and so on. They make little tracks. But later on in life, when we study more about electrons, we learn that actually you can also think about electrons as being waves. This is important when quantum mechanics is involved. When you have quantum mechanics, then electrons aren't really particles anymore. Instead, they sort of satisfy a wave equation called Schrodinger's equation. So if you ask, what is an electron? Is it a particle or is it a wave? The answer is a little bit confusing. The truth is, it can really be both. It really depends which question you're asking, and that determines which description, if it's in terms of particles or in terms of waves, is more important. Now, from that point of view, the subject that is elementary quantum mechanics of the sort you learn in your class, it's all about the duality between waves and particles. Okay? So this lecture is going to discuss something different. It's going to be a duality involving quantum gravity. So quantum gravity might sound a little bit scary. Let me sort of try to explain why it might sound a bit scary. You see, the word quantum, we typically associate with very small things, electrons orbiting nuclei, very small things that are all tiny and fuzzy. Whereas gravity is normally associated with very heavy things, galaxies, black holes, for example. Here's a picture of a black hole. And when you have these heavy things, then the way to think about gravity is that it curves the fabric of space and time. Now, in elementary physics, we normally don't think about these two ideas together. And that's really because small things normally aren't very heavy. But let's push on and try to understand a little bit anyway. So you might have heard that quantum gravity is confusing. So let me try to tell you about one aspect of why it's confusing. When quantum mechanics is involved, then the main point of quantum mechanics is that things fluctuate. So for example, here is maybe a wave function of some electron. I'm calling it psi. And what this wave function means is it has some sort of spread in space. And that means that it's not true that the electron is going to be in only one place. There's a probability to find the electron in many different places, and that is what is measured by this wave function. In other words, there's some sort of intrinsic fluctuation associated with the quantum mechanical description of the electron. No matter what, it fluctuates a bit, and you just cannot stop that from happening. Now, what about gravity? Gravity tells us that the fabric of space and time can curve. A heavy object, through Einstein's theory of general relativity, will curve space and time will tick differently near that object. So what this really tells us is that space and time itself is a dynamical degree of freedom that can change when gravity is important. So if we know that space and time is a degree of freedom, and if we know that degrees of freedom fluctuate, then the combination of these two things would tell us that the fabric of space and time itself will fluctuate. And this is just basically kind of a confusing idea. What does it mean for space and time to fluctuate? What is really going on? So this is basically why quantum gravity is so confusing. And I now want to try to understand one very specific sharp example of this confusion. So let's consider one of the simplest objects that exists in general relativity. It's a black hole called a Schwarzschild black hole. Now, some of you who are watching this might have some exposure to general relativity, in which case you know this formula. This formula describes the curvature of space and time near a Schwarzschild black hole. But if you haven't seen general relativity, that's okay. You don't really need it. I'm just putting this formula here to show you that there is a simple formula describing how space and time look near a Schwarzschild black hole. It's simple enough that I can write it in one line. It has some parameters in it. Here, m is a parameter, which is the mass of the black hole. G is Newton's constant. Okay. And for example, this dt means that we're looking at how time ticks near a black hole and so on. Now, I think everyone knows one basic fact about black holes. There is a sphere surrounding the black hole called the event horizon. The event horizon has a radius, which is given by 2 times g times m. And the special thing about the event horizon is that if you are living your life happily, but you happen to cross the event horizon of the black hole, then you can never escape again to the outside world. That is why black holes are called black, because they suck in everything, including light. Okay. So this is the basic point about a black hole that I think everyone knows about. Okay. So now what I just showed you was the simplest kind of black hole, but it turns out there are other kinds of black holes. Let me just tell you about them very briefly. There are things called charged black holes. So you know about electric charge. It turns out black holes can carry electric charge. Here you can see some electric field lines coming out from that black hole. And the electric charge is something I'm going to call Q. Okay. These charged black holes are called Reisner-Nordstrom black holes. And you can also have a black hole who rotates. Black holes that spin exist. And they have some angular momentum, which I'm going to call J. And these black holes are called Kerr black holes. Okay. So now, let me tell you one profound and kind of counterintuitive fact about black holes. It turns out that any black hole can be completely characterized by these three numbers: the mass of the black hole, the charge of the black hole, and the angular momentum of the black hole. This is a theorem which is sometimes phrased as saying that a black hole has no hair. You cannot put some sort of a hairstyle on a black hole. You can't decorate it in any way. It only has these three numbers describing it. So let me stress that this is very different from normal objects, like planets, for example. So like here, for example, is a planet. The planet has people on it, and you can put all different kinds of people on the planet. You can decorate the planet in some way. It seems like I've given it stripes in this picture. Or you can have a different sort of planet. This planet might have dinosaurs on it and a polka dot sort of decoration scheme. And you see all this information describing what is on the planet, what you've painted the planet with, all things like that. All that information describes the planet, but you see, it does not describe a black hole. A black hole cannot carry this sort of information because it's described only by these three numbers: the mass, the charge, and the angular momentum. There is no space to say that it has this many people on it, or the color scheme is this, and so on. And in particular, if you take this planet and this planet, which look quite different, and if you collapse them into a black hole, it appears that that black hole will lose the memory of what was there before it collapsed. It'll only depend on the mass of the final state, okay, and the charge and so on. Okay, this is very different from ordinary objects. So does this disturb you? It probably should. So let me tell you why this should disturb you, and in fact, why it's probably not completely correct. So let me remind everyone about the notion of entropy. Okay, you've all learned about this in your thermodynamics or statistical mechanics courses. So imagine taking a box of gas. Okay, so here's a box that's full of little gas molecules, and the gas has a few numbers characterizing it. It has a pressure, it has a temperature. And in statistical mechanics, we learned that this box of gas has an entropy. The entropy is given by Boltzmann's constant times the logarithm of the number of microstates of the particles in the box. Okay? So this basically tells you about how many different things that the particles in the box could be doing. That is what the entropy measures. It's Kb times log omega. Now, this box has some entropy, and we've probably all calculated this entropy at some point in our lives. And in life, it's a fact that the second law of thermodynamics tells us that the entropy should always get bigger in all physical processes. The entropy can only increase. This is basically a manifestation of the idea that as life goes on, disorder tends to increase. Okay. So now let's think about that, the box of gas and the entropy, in a framework that has gravity in it. So let's do the following thing. Let's take our box that has some entropy. Okay, so here's a box of gas. Take our box of gas, which has some entropy, given by Kb times log omega, where omega is the number of microstates of the particles in the box. Let's take this box and let's hold it near a black hole. Okay. So let me figure out what the entropy of the two different things is before we drop the box in. So that box has some entropy, first of all. Does the black hole have any entropy? So at first, you'd be tempted to conclude that it does not. Let's try to understand carefully why. The entropy counts the number of possible states that the black hole could have, but we know that the state of the black hole is completely characterized by the mass of the black hole and its charge and all these things. In other words, it's completely fixed by these three numbers, and so there is only one possible state that the black hole could have, and its entropy therefore is zero because the log of 1 is 0. Okay? Okay, so this is the setup at the beginning. And now let's take this box of gas and drop it into the black hole. Okay, the box will get eaten. The black hole will get a little bit bigger. Its mass will go up a little bit. But, the entropy afterwards it's still zero, right? Because of this no-hair theorem that tells us there's only one microstate attached to this black hole. So in other words, it looks like the entropy at the beginning, which was non-zero, is now zero afterwards. And the second law of thermodynamics has been violated. So this is very disturbing that the second law of thermodynamics can be violated, that entropy can go down when black holes are involved. So this is a perplexing fact that confused people for a while. So let me push on this a little bit. Let me first take a step back and consider the area of the event horizon. So you can calculate this with normal formulas. The area is equal to 4 pi times the radius of the event horizon squared, just like the normal formula for the area of a sphere. And the radius, I told you, is 2gm. So now here's the thing you can do. If you imagine varying the mass of the black hole a little bit, then the mass of the black hole will change in a certain way, and the area will also change in a certain way, which you can figure out from this formula. Okay, so you get a formula that looks like this. dm is something times dA. Now, this something turns out to be, in general, called the surface gravity of the black hole. It measures sort of the acceleration if you're hovering at the black hole horizon. It measures how much acceleration you will feel pulling you into the black hole. And in fact, normally we call this surface gravity kappa. And it's a fact that for any black hole, which you remember is completely characterized by the mass, the charge, and the angular momentum, we can write a formula that looks like this. dm, m being the mass of the black hole, is equal to kappa, the surface gravity, times dA, plus something else times dJ, plus something else times dQ. And this expression, which you can derive by doing some general relativity type stuff, is called the first law of black hole mechanics. Okay. To some of you, it should already be clear why this is called the first law, but let's just keep this in mind while we look at the second law of black hole mechanics. So next, I want you to imagine the following experiment. Let's take two black holes who have mass m1 and m2, and let's smash them together. Okay. So what is the initial area of the two event horizons? It's a1 plus a2, so it's basically m1 squared plus m2 squared. Now, what is the area of the final thing? Now, this actually depends on exactly how you collide them. The truth is, if you smash them together, it'll be a very violent process that will result in a lot of energy lost in the form of gravitational radiation. But let's actually imagine doing it very, very gently and very slowly, so that no energy is lost. In that case, the mass of the final black hole will be roughly m1 plus m2. And the final area is going to be given by the radius of the new event horizon squared, which is m1 plus m2 squared times some constants. So notice that the area of the black hole afterwards is bigger than the initial area, okay, a1 and a2. Now, in this example, this is a stupid example. It just has to do with how quadratic expressions work. But it turns out it is a theorem due to Stephen Hawking that no matter what you do, no matter how you smash these black holes together, no matter how violent of a process you do with black holes, the area of the event horizon will always go up. It will always be bigger at the end than it was when you started. Okay, so dA dt is greater than zero always. And this is called the second law of black hole mechanics. Okay. So these are two laws of classical general relativity. And of course, the point is that these laws should remind you of the ordinary laws of thermodynamics that you studied in your thermodynamics class. What is the first law of thermodynamics? Just to remind you, it is dE equals TdS plus mu dN, okay? Where T is the temperature. Now, E is the energy, but remember this famous formula from Einstein, E equals mc squared. What that means is if things are at rest, the energy and the mass are basically the same. And in fact, everywhere in this talk, I'm going to be measuring things in units where the speed of light c is 1. So in other words, E is the same thing as m, and thus this expression here looks a lot like this expression here, provided I'm happy identifying some of these things with entropy, okay? Now, which of these things should be entropy? Here we get a clue from the fact that in the normal second law of thermodynamics, the entropy always goes up. And what we found previously was that the area of the black hole event horizon always goes up. So in other words, we should identify area with the entropy. In that case, these laws, the laws of black hole mechanics, look pretty much exactly like the ordinary laws of thermodynamics. Okay. So notice that this also suggests that the thing multiplying ds in the first law, let me just remind you what that is. That's this thing right here, this kappa, should be viewed as some kind of a temperature. In other words, if we take this seriously, this suggests that the black hole has not only an entropy, but also a temperature who goes like the surface gravity of the black hole. Okay, these ideas are crazy, that an entropy could have an area and that it could have a temperature. And for many, many years, people just thought that this was just a sort of analogy, like a mathematical analogy between two different systems that just happen to look kind of the same in terms of these formulas. So we now think that something much, much deeper is going on. And this again comes from something due to Stephen Hawking. What Stephen Hawking showed is that if you combine a little bit of quantum mechanics, or more precisely quantum field theory, with general relativity, something very interesting happens. So let me just give you a very heuristic idea of what's going on. If you include quantum mechanics in your description of the universe, then it's a fact that what we think of as empty space is actually full of particle-antiparticle pairs sort of appearing and disappearing and so on. Now, here's something that can happen, or here's a way to think about something that happens near a black hole event horizon. Let's imagine I have a black hole event horizon shown by this dashed line. Then you can imagine that it's possible to think that a particle-antiparticle pair is created near this event horizon, and then maybe the particle falls into the black hole, but the antiparticle comes out of the black hole. Okay, this is something that can happen, and if you look at it happening over and over and over again, and you zoom out, then it'll look like the black hole is just spitting out particles. Okay, these particles right here. And in fact, Stephen Hawking showed that not only does it spit out particles, it spits out particles in exactly the same way as a hot object, as ordinary black body radiation, with a temperature given by h bar times the surface gravity kappa. Okay? In other words, all black holes have a temperature called the Hawking temperature. Okay. And it's given by exactly what we would have expected from our sort of thermodynamic analogy, except that we now know there's a factor of h bar in this formula, where the h bar is there because now we're doing some quantum mechanics. Okay. So now, let's remember the first law of black hole mechanics. It said dm is something times dA. We now know precisely how to isolate the part of the something who is the Hawking temperature, which means we can figure out exactly what the part that should be S is. And what we conclude is that the black hole has an entropy, which is exactly given by its area divided by 4 times Newton's constant times h bar. This is called the Bekenstein-Hawking entropy of the black hole. And this is really a very profound fact. It tells us that black holes have entropy. There is something going on. There are some microstates that we can count. And when we count them, the number of them is exactly given by this formula. Where I'll stress that this is an exact formula in that there's really a 4 here. It's precisely a 4. It's precisely Newton's constant and precisely h bar appearing here. So the event horizon goes like the area of the black hole. Sorry, the entropy goes like the area of the black hole. Okay. So now let's think about this for a second. Let's think about the implications of this Bekenstein-Hawking entropy for our understanding of the world. So first of all, the complaint that I had about the second law, it basically goes away. So from now on, I'm going to set h bar to 1 to avoid writing it over and over again. Let's now imagine doing our same experiment again. Let's take our box of gas, which has some sort of initial entropy, and now we hold it near the black hole, who has some initial entropy. The difference is the initial entropy is no longer 0. It's now given by the area of this event horizon. And now you drop the box in, and the black hole gets a little bit bigger. And now it still has entropy. The new entropy is given by A2, the area after the box fell in. And so we now see that we can save our second law if we just demand that the area of the final event horizon is always greater than the area of the initial event horizon plus the entropy of the box of the gas. This is called the generalized second law of thermodynamics. It's how you should think about thermodynamics near a black hole. And this you can show under many situations is actually true. Okay. This seems to be a true fact about nature. This is always upheld. Okay, good. But now, this entropy is a little bit odd, okay? So what is odd about it? Let's go back to our entropy of our box of gas. The entropy of all ordinary systems basically goes like the volume of the box, okay? And I think people have done this calculation, so you know that this is true. It goes like the volume, and there's some factors of temperature and so on. But the fact that it goes like the volume is really a very basic idea, okay? It sort of has to do with the way you think about spatial locality inside the box. It goes like the volume basically because the particles can move in a volume, or said in a slightly different way, at each point in space, there's a couple of different things that could happen. And that's why the entropy goes like the volume of the box, okay? But the entropy of the black hole is very different. It doesn't go like the volume of the black hole, whatever that means. It goes instead like the area of the event horizon of the black hole. In other words, it doesn't depend, it looks like it doesn't somehow live in 3 dimensions, it lives instead in 2 dimensions. In other words, the black hole states somehow, this counting is suggesting that the black hole states live in 1 lower dimension. So now, if you've been following along, you should have a very natural question. When we do statistical mechanics, we know that entropy counts a number of microstates, and we know what those microstates are. For our box of gas, there are exactly all the different ways that the particles can move around inside the box. But what are they for the black hole? What are the microstates that make up the black hole entropy? And why does it seem like they live in 1 lower dimension? This now is the new mystery, and this is now something that we have to understand. And I'll explain how to understand it in the second video in this sequence. Thank you.